Hi, and welcome to the Improv Digital Modules on Geothermal Environments. My name is Cristian Montanaro, and I will be your teacher for this module. The module will be divided in three parts. In the first part of the module, we will explore the various types of geothermal manifestation and the associated hazard. You will learn about features such as hot spring, fumarole, collapsed structures, hydrothermal eruption, and so on, as well about the potential danger that they pose to infrastructure and people. Through this module, basically you will gain a comprehensive understanding of dynamic and sometimes hazardous nature of geothermal areas. Firstly, I would like to define a geothermal and hydrothermal system. While I will not go too much in detail about the types, properties, and examples, I just want to highlight that these terms are often used interchangeably but have different meanings, as proposed by Jackson 2005 and his Glossary of Geology. Geothermal refers to any system that transfers heat from within the earth towards the surface. And this schematic here is just like represented what I meant. So we have like a heat source deep in the crust which reaches the shallow part of the crust where the fractures present in the brittle part will allow the presence of permeable rocks, which in turns allow for heat to flow towards the surface and produce a geothermal anomaly. Geothermal systems are common in high flow areas near plate boundaries and hotspots and can be classified mainly as five types. We have young, igneous system over shallow magma, tectonic system with fault fluid circulation, deep sedimentary aquifer, hot dry rock systems, and supercritical and magma top systems. Intrusion-related systems are usually the hottest, while the extensional environments are the ones supporting extensive fluid circulation and good reservoirs. Hydrothermal is a subset of geothermal, implying that the heat transfer is mainly operated by water through convection, and in which water can have liquid or steam state. Hydrothermal fluid circulation around stratovolcanoes, calderas, and rift zone connects magma to the hydrosphere using heat, permeable rocks, and water. Basically, this is a schematic of what I was just defining, and you have like magmatic source of depth within a sort of like a ductile domain. While reaching the brittle domain, it creates a permeable reservoir. Permeable reservoir is mostly dominated by fractures produced by tectonics process and the hydrothermal fracturings. These allow basically the water or meteoric water or seawater to penetrate down into the ground, reach or approximate the heat source, and then enter the circulation system. Clay seals are often present in hydrothermal systems, and they basically allow to separate or isolate the shallow groundwater aquifer that contain mostly cold waters. Temperature in this kind of hydrothermal system can go from 220 up to 350 degrees C in depth between 1 to 3 kilometers. All this information are provided by the fact that we have lots of geothermal exploration around the world, and we also have like some hydrothermal exhumed system which provide fossil analogs for active systems. Geothermal environments are known for their unique features such fumaroles, colorful lakes, bubbling pools, hot spring, mud pools, and rich mineral deposits. You can see one example here below with the Champagne pool in Waiotapu in New Zealand. And these fascinating characteristics, they attract tourists which are interested in geology, nature, and adventure. But additionally, geothermal environments, they provide also valuable geothermal energy source or resources which are increasingly important in a time where we are looking for sustainable energy. And this is just another example here where we have the Krapla power plant in Iceland, which is one of the best example of our we can exploit geothermal energy to sustain, for example, the electrical supply of many cities in Iceland. Geothermal environments are very dynamic due to the fact that changes in pressure and temperature can happen because of natural phenomena or human activities, and these changes can result in variation of the system behavior. Natural pressure fluctuation can include phenomena like groundwater levels dropping during droughts, or like reduced water mass during lake drainages, or because, for example, landslides removing rocks. Some subtle variation or changes can also occur from extreme weather events, which can cause pressure lowering, for instance, during on the passage of a cyclone. For concerning the temperature changes, these are mostly due to the injection of magmatic or hot deeper fluids, which they lead to, let's say, they can lead to rapid increase in temperature all around geothermal areas. Human activities such as injection and extraction in geothermal power plants can also cause changes, for instance, in the aquifer pressure. Modern companies monitor and manage this process to avoid significant impacts, like in the past where uncontrolled operation often cause hazardous physical changes and, let's say, damage. Overall, variation in pressure and temperature can produce a variety of physical effects, which we're now going to explore, and some of them can represent a hazard to people and infrastructures. Concerning the physical effect from pressure reduction and temperature increase in geothermal environments, these can vary in time and in scale. Common effects include increased boiling in aquifer, leading to more steam formation and ground weakening. Reduced pore pressure during fluid extraction, for instance, can cause sediment compaction, which combined with ground weakening can contribute to ground subsidence. Finally, changes in surface thermal activity, such as variation in fumarole or spring temperature, or the formation of new features, can also occur. In extreme cases, rapid decompression or sudden heating can even trigger hydrothermal eruptions. So let's just have a look to some specific examples from some of the study cases to show the phenomena we just described. In this first case, we're going to look at Rotokawa geothermal field from New Zealand. This area has been characterized by mining activity for extraction of sulfur, native sulfur. While doing that, basically they've removed part of the clay cap which was covering the hotter part of the system below, and this resulted basically in the increased emission hot gases, which in turn caused the thermal stress on the ground and led to the mineral deposition as well as the formation and widening of weakened and unstable soil areas, which can be seen like in this picture here. So area that before might have looked like this, change it in something like that with expansion of small fumarole and vents depositing native sulfur and the formation of very unstable and weakened ground. Here is another example from Pisciarelli, an area northeast of Solfatara in Campi Flegrei in the area of Naples. Before 2006, this area only had minor fumaroles and a mud pool, and this is like a picture from 2005 showing the area. You can see the small mud pool and the main fumarole. However, since the unrest phase, which began in 2006, the overall CO2 flow has increased throughout the Solfatara and Pisciarelli areas. And the surface activity in Pisciarelli, including steaming ground, fumarole springs, and mud pool, has increased in number and in size. For instance, the small main fumarole that you saw here has been transformed in a very powerful gas jet, and the small mud pool have spread out to form like a sort of a mud river that we can see here, and produce occasional and dangerous bursts of hot mud like in this picture. And additionally, much of the soil in the area, which we might kind of see here and in this part or in this part, has become very unstable, and especially on the slope behind the area, and sometimes also trigger landslide phenomena. Here is another example from Rotokawa. We can see the effect of intense acidic alteration. Such alteration can happen in vadose zone, so the area above the groundwater level, where the low pH steam that contain a lots of like H2S with a temperature around 120 degrees C or below start to condensate. And this process, which is also known as advanced argillic steam heated alteration, produce native sulfur analog with clay-rich and hydrothermally altered rocks. And these are like two examples of this process. You can see the intense alteration and the halo around the potential fumarolic zone, and produce very weak and unstable ground, which usually tend to, or they are prone to mechanical failure. In this example, again from New Zealand, but from another area called Tikopia, we see one consequences of the acidic steam alteration, where in this case, basically the process occur over a high relief area and on a very steep slope along the fractured zone that we can kind of see here. So this is the kind of the cliff of about 80 to 100 meter in some spot, and is along a very big fracture system. So the fractured area allowed for the condensate acidic fluid to weaken a large part of the upslope, resulting in several large landslides, which came down, well, sequentially in time, while basically the fracture was moving and the altered rock were falling down. And you can also see like the size of this landslide by looking at the size of the Professor Shane Cronin hiking over one of the main bodies. And what is remaining nowadays is like also this quite spectacular and fuming landscape. Returning to Rotokawa, here's an example of dissolution or collapse crater. In this case, the intense leaching of material just above the groundwater table likely created a subsurface cavity and below the ground. So basically you have ascending gases which start to dissolve the rocks below. And well, over time, these cavities can destabilize and lead to the formation of a large collapse on top of it. And this collapse can also grow in time as the edges continue to collapse. Normally, this feature can form where there are lithological or structural discontinuities at depth that allowed for ascending gas to dissolve the rock and weaken it from below. This is just one example from Rotokawa Taupopamis deposit, which is the most widespread deposits around the geothermal field. And this is one beautiful example of a collapse structure which is about 15 meters deep. And basically you can imagine again the groundwater table to be at sort of this level, and what was before the full deposit, volcanic deposit, was eroded from below until the time it's collapsed down. Here we have a map showing isolines around the geothermal field of Tauara and Wairaki in central North Island, New Zealand, close to lake and town named Taupo. These isolines basically represent the subsidence anomaly which were measured during the period 2004-2009 through the borehole in the geothermal fields. Now, in these geothermal fields, like in many others in New Zealand, these anomalies are linked to the presence of relatively shallow, unusually compressible porous formation, which are generally weakened by hydrothermal alteration from boiling fluids, in particular when these produce intense argillic alteration. The other reason, or the other process which is also used to explain this anomaly in combination with alteration is the fact that the extraction of fluids from the deeper part of the aquifer produce deformation which slowly diffuse to the shallow into the shallow aquifer and aquicludes. So a combination of clay formation and ground or rock weakening together with reduced pore pressure and compaction, it can produce subsidence over like a quite wide area, as you can see from the scale of these two geothermal areas, and result also in subsidence in this particular case that goes down, well, up to 100 millimeter per year. The most dramatic consequence of perturbation in geothermal areas is the occurrence of hydrothermal eruptions. These eruptions are usually triggered by sudden changes in pressure or temperature and causing the hot pressurized water within the aquifer to flash into steam and expand. The energy associated to this steam expansion can overcome the strength of surrounding rocks, fragmenting and ejecting them. Here we have two examples, one from Mount Tongariro in New Zealand and one in Iceland at Lake Kinkisik within the caldera of Kverkfjord. The eruption occurred 1 year apart, Tongariro in 2012, Kinkisik in 2013, and they were quite different in terms of size and dynamics. While the eruption at Kinkisik was triggered by a lake drainage over the geothermal area, at Mount Tongariro, the hydrothermal system was perturbed by the occurrence of landslides, which unroofed the hydrothermal system. At Kinkisik, the eruption were quite include a series of explosions which were quite small and produced like a series of debris ejecta, which were deposited mostly around the craters, with a very few ashes dispersed over maximum 1 kilometer from the vent. At Mount Tongariro, the eruption was the scale of the eruption was much larger. The eruption produced a series of pyroclastic density current, ballistic showers with ballistic reaching distances of 1.4 kilometers from the source, and a large ash plume which was dispersed over square kilometers away from the main vent. The main issue with these eruptions is their unpredictability in terms of timing and magnitude. Not to mention that it's also very hard to predict where a location of explosion can be in geothermal environments. Although the example mentioned before, like Tongariro and Gingisik, did not cause any casualties, recent eruptions like those at Mount Ontake in Japan in 2014 or Fakari White Island 2019, they resulted in approximately 100 fatalities. You can see here the number for all the Fakari Island. There were at least 21 people dead and 26 injured. In both cases, most of the people which were killed or injured, the primary reason was the vicinity to the crater and to the direct blast, or to be impacted by one of the ballistic blocks. To summarize, there is here this table that classifies the main hazards in geothermal environments and details their extent and their impacts. Although I didn't explicitly discuss or provide an example, geothermal gases, they pose significant risks, and particularly hydrogen sulfide or carbon dioxide, which are toxic and can cause suffocation. Another hazard is the degradation and failures or infrastructures, for example, in tourist areas and in power plants, which can potentially endanger people with exposure to hot fluids or gases. Now, I won't delve deeply into this list here, as a comprehensive information and more detailed discussion can be found in the paper of Fitzgerald et al. 2022, which I highly recommended. It's important that you note that many of the hazards can range from localized to have a localized impact near to the source to a broader effect. Again, like for example, the deterioration can be confined to infrastructure, ground collapse confined to, again, the extent of the structures, which can be tens of meters, but heated ground is going over the whole geothermal areas, which can be square kilometers, and so on and so on. The most significant hazard, which I did not mention, is not mentioned again in this list, but which I discussed just before, is hydrothermal eruption. which product can extend from few meters to hundreds or even thousands of meters. And also this eruption can pose risks like burn from fluid, steam, pyroclastic flows, and ballistic projectiles. And gas are also emitted during such events. So that's the complete list of hazard from geothermal environments. Okay, now that we discussed most of the thermal feature and which can be found in the geothermal areas, and also have seen the eventual hazard some of them can represent. Now we want to know how to, well, we can characterize and quantify the properties of these features, and also try to understand how changes in these properties related to specific feature and due to changes in temperature or pressure in the system can be tracked down. So we saw that many of the geothermal features we shown and discussed, like fumarole, hot spring, mud pools, and area of heated or unstable ground, are located on the surface. Some of these features have alteration halos that can affect both top and subsoil. Like in this uh, picture shown here, this is just one example of subsoil around the Krapla geothermal field, and we can see kind of like intense coloring of soil layer due to the fact of the vicinity to thermal feature. But we'll come back to this point later. And so while for soil the alteration alloy can be quite limited in space, like few decimeter or meter, for collapsing structure this alloy can extend over meters or tens of meters within soil and rock formation. So these thermal features as well, they're always linked to some structure at depth. So as I said, there's the local geology controlling the location and the presence of fault and fracture system, which act as a pathways for fluid to move from deeper layers to the surface. So understanding the distribution of thermal feature at the surface can help us to link them to what happened below. As well, over time, the interaction of fluids with rocks and soil change the properties of the soil. And the properties which are changed are mostly permeability, porosity, and strength, which in turn they can affect or alter the fluid circulation and the superficial degassing pattern, and as well changes in the distribution or formation of new thermal features. So the main point here is like, how do we look at it? And I'm gonna show you some of the our field-based approaches to do so. So in this first part of the module, our focus will be on mapping and identifying the types of geothermal features found in the Rotokawa field. I also will be giving you some geological constraints or information which, implemented together with the mapping of the thermal feature, helps to understand eventual correlation between the superficial thermal distribution with the shallow geology or the presence of fracture system. And the second part of the modules, we're going to be looking more on the characterization of soil, mapping, and distributions of soils as well, again in the area Rotokawas. While in the third part, we're going to have a look on a bit more detail in the Krapla geothermal field, with also some example of laboratory study included in the discussion. Here there are thermal features from both Rotokawa and Krapla geothermal fields. You can see a variety of hot springs with mineral deposits and the effect of acidic alteration and collapsing structure from Rotokawa, as well many cases of degraded soils and heated ground and fumaroles and acidic steam heated alteration from Krapla. The Rotokawa geothermal field is located 15 km northeast of Lake Taupo in the New Zealand's Taupo volcanic zone. It has a high temperature resource exceeding 300 degrees C in the deeper part of the system, and a series of northeast-southwest fractures which allow for deeper fluids to enter the hydrothermal system. which is rich in gas as CO2 and H2S, which can also be in high flow of these gases can be measured at the surface. The mixing of shallow boiling fluids and groundwater creates basically acid sulfate and bicarbonated fluids, which are leading to the deposition of native sulfur and a variety of minerals which can be found in Rotokawa. The subsurface geology include the Taupo pumice, which was erupted by the last of the Lake Taupo eruption, that together with some Holocene tephra is mantling or filling up the craters of older hydrothermal eruption. Here you can see the border of the craters from the past activity before Taupo pumice. And of course the geology include breccia itself erupted during the eruption as a breccia outside the crater and fallback material. In terms of like thermal areas, there are two main thermal areas in the Rotokawa field. One which is outside the map but is located more or less here. It's like the northern area. The feature includes few chloride bicarbonate springs along the Waikato River and a little bit of steaming ground areas. In the southern area, the key feature is the Lake Rotokawa itself, which is like an acidic sulfate lake in filling up one of the largest hydrothermal crater area. Nearby there are hot springs and fumarolic fields and collapsic structures. This area is called mostly it's been defined as the steam field and correspond to the mined area during the 1960 to the 1990 where they were extracting sulfur, native sulfur. And then we have like a series of fumarole and spring along the Parariki River, which is the one departing from the lake going northeast along one of the eroded crater, and sulfur cliff, which is an area of intense fumarolic activity and mineralization. So the steam field area includes a large variety of geothermal features, and the detailed mapping we carried together with in situ analysis allowed us to distinguish three main spatial domains based on the prevalent group of geothermal feature, the soil types, and the apparent differences in alteration. These are named Domain 1, Domain 2, and Domain 3. Moreover, by using historical maps and photos from the past 70 years, together with like the LiDAR map collected a few years before our surveys, we were able also to better define all the area which were strongly affected by the mining activities. So Domain 1 covers most of the eastern steam field area, with the feature which aligned somehow northeast-southwest direction. In the central and northeastern parts, there are many natural collapse structures like the one we can see in these pictures, and some of them with spring or pool at their base. This is one example with like a quite large pool, and there is also a small pool in this picture which cannot nicely be seen, but anyhow. The pool can contain fluids which are milky or turbid in color and can show mild to intense bubbling and degassing. The collapse pit can range from 10 to 30 meter in diameter or merge into larger structure up to 45 meter wide, like in this example. And the depth is decreasing from 10 meters in the northeast to 6 meters in the southwest, getting close to the lake. Around these collapse structures, there are often excavated areas, like in this example and in this example, which can contain sulfur cemented ground structures, steamed and heated ground with the scattered fumarole. Even though you cannot really see it here, because of the scale of the picture, there are many small spots where gas is coming out from the ground. Unstable ground all around the area is made of altered or reworked material, which is usually found between collapsed structures. In the southwestern part of Domain 1, there are a series of springs and pools of various composition, which can be found mostly in depression, were formed by mining, so within excavated sites. Among the many features, there are some which are quite striking, showing quite unique feature. In this example here, which is not formally known as the Middle Earth, We have a combination of like milky green waters, blackish mud pools, sulfur-rich deposits, fumarole, which are not visible now, but there are quite active fumaroles from small vents, and there are intensively degassing quite large pools, and so on and so on. And then we also have like additional features like in the close by springs, where we have a combination, a mix of water springs, like clear or greeny water springs combined with muddy pools in a kind of rectangularly shaped escape area, which is clearly another excavated feature, which it's not easy to see from this example here, but when you see the map in plain view, it's quite easy to recognize. Domain 2 is centrally situated within the steam field area and is characterized by a prominent east-west oriented spring area along the northern border of the lake, and which is known as the lagoon, as already mentioned before. This area hosts in its eastern side like a series of continuous pools of milky water which display intense bubbling, often surrounded by microbial mats or stromatolites like the one showing here. In its central and western side, on the contrary, there is the presence of large distributed muddy sinter deposits with hot spring emerging in a similar spot, as we can see here and here. And here you can also recognize somehow a sort of like a lamination, which is like all the different layer of mud, and some of them cemented by sulfur. In the northern and western area of domains 2, natural water, spring, and mud pools and collapsed structure can be found. Even here, mostly of the feature where feature developed are within excavated site, as in the picture shown here. In this area in particular, one of the large feature on the western part of domain 2, you can find a large amount of turbid to muddy waters with bubbling and slight to highly degassing feature. In some other area, you can find more springs with like milky colored or like or crystal clear color with intense bubbling and slight degassing. And amongst many of these areas, unstable ground can be found together with encrusted ground, which sometimes can occur over like the tracks of machinery used at the time. I think I'm going to show you later some example. Domain 3 is in the northern part of the steam field area and includes various features such as scattered depression, collapsed pit, shallow excavated area, and a long, narrow depression. And this last feature is here in this picture. It's superimposed to an older crater rim and is located at the geological boundary between the Taupopamis, which is this deposit, the bedrock, which is like old ignimbrite Oroanui deposit, and on top of this, covered by the vegetation, there is like one of the Parariki Breccia deposit erupted by the eruption crater located in this area. The area contains also degassing depression, collapsed structures, bubbling pools, ground cemented with sulfur, fumarole steaming into the ground. These are just some examples of the collapsed pit all around, which are quite spectacular with this oxidation, stains, red color. Cannot be seen here, but there's a very intensively bubbling feature below this depression, which is named Rainbow Crater. And yeah, some part are highly altered and friable and unstable, are all around the collapsing feature, and these are kind of like a dominant component of the domain tree. So just to summarize, it's mostly rich in collapsed area. All the collapsed area contain a different degree of degassing fissures or bubbling pools, and most of the area around it are characterized by very disaggregated or unstable and thermally stressed ground. Here we have sulfur cemented grounds. They form all over the three main domains, and they are recognized or identified based on their texture, structure, and physical properties. These grounds typically form on top of talc-pumice deposits or over mixed rework material from mining activities. The flat cemented ground, we have an example here, are quite hard, thick layers spread over large areas and can be found in patches with surface patina and degassing cracks. Cemented pumiceous mound and tracks form around excavated areas, heated and degassing sites, and with sulfur precipitating on network or reworked material or machinery tracks, as you can see in this example. It's quite spectacular pumice-rich reworked material with sulfur filling up cracks and space between pores, or in this case where the sulfur precipitation basically frozen, which was the thread tracks of the machinery. And in this other case, you can nicely recognize the amount of piled material from excavation lately being cemented. Even in this case, we can always recognize a sort of a crack in between and the patina on the sides. The last type of cemented ground is the crusted hummocks. They are mound shaped with superficial patinas and cracks. Usually you can find main cracks, but sometimes sort of like lateral or parasitic cracks and small degassing bands. And often they also show layers which are dominantly filled up with native sulfur, or sometimes, or most of the time, native sulfur is filling up space between grains. And you cannot nicely see in this picture. When you zoom in, you can see that. And by cutting, making a cutting through this ground, we also managed to see how this material or this structure was kind of fed by fluids probably rising through the gassing pathway in the soil below. Here we have like a close-up snapshot of the map we produced after the survey in the steam field area. You can recognize that many of the features we've been discussing, and I've been showing you the example so far. And in the legend, they also reported different spring and pools that we can see, for example, distributed close by the Lake Rotokawa area. Or we can have sulfur cemented ground, which apparently is distributed in many areas all around the three domains. Then we have like unstable ground and collapsed structures, which usually go together. Unstable areas are quite extensive as well. You can see in these different parts. And then we can have like in other parts, but more external to the steam field, bodies of cold waters. The most prominent feature probably in this snapshot, and they will see in the map in the next slide, is the presence of these patches of dark color or dark gray, which are all the mined areas. You can really see how basically the feature they fill up most of these mining areas. So here is the final map. Now you can see the full steam field area with the distribution of, again, all the main mapped features. The mapping revealed that the geothermal features are concentrated in specific areas, with the influence diminishing quite quickly away from this zone. So it's sort of like you can see, recognize a sort of alignment between domain 1, domain 2, which is sort of northeast, southwest, as well as like in domain 2, domain 3. Domain 3 in particular is a feature which is more like west-east directed, and so on and so on. So before mining, this feature might have had the same characteristic, or they were in the same place but being less extensive. After the mining, the new thermal feature quickly appeared and distributed all over the disturbed land. Gas emission, fumarole, sulfur deposits, and crust form all across the thermal area. Excavated area also reveals that many sulfur encrusted structures forms quite quickly after the mining activity. Warm springs and pool were found. Seems to be quite distributed in the area close to the lake, Rotokawa, while hotspots around this pool can be seen building up a lots of mineral deposits on the edges or sinters. Many mud pots in the depression seems to be forming by lots of dissolution of the rock through acidic fluids, and as soon as the terrain rise, or well, the morphology is let's say quite elevated above the lake level, you can see the dominance of collapsing structures, where basically above the steam, where the terrain rises above the water table, the action of the steam, acidic steam weakens many of the rocks, causing this collapse. And also we have hard ground layers that act as insulator, masking some of the high subsoil temperature in many of these areas. So one last thing is that during our mapping, we also collected soil samples and classified them based on their properties and compositions. And these data help us to develop like soil profiles from key site and in the steam field, and this allowed us to understand the fluid and temperature distribution and so on. But more of this will be discussed in detail in the second part of the digital training module. So here we conclude part one, manifestations and hazards of the digital training modules, geothermal environments. Below you can find the literature cited through the slides, and in addition some further readings. I highly recommend to go more in details and in depth in some of the argument discussed through this module. I thank you all for following along, and I'll see you in the next module.